Okay, I stopped here. That it means that we said for the velocity, the vector v, which is the velocity, has always one component, which is in tangential direction. And if we look to the acceleration has the projection of the magnitude in tangential direction and one component which is the normal one. That it means this component is normal to this one. It make angle of 90 degree. Now, if you look to definition of the acceleration is the velocity dot, and we have here the tangential one as it's in tangential direction. If we make the equalities, yeah, v dot, then we have v dot et and v dot will be only the acceleration in tangential direction. Then we have here dv over dt, and as the velocity is time dependent, and also it's depend on the angle phi. Then we have, I will take once again the tablet, and we have here, if I write, I can write that it's dv over dv multiplied by dv over dt. And you see there is a difference when I use the browser. You can see the writing, it's the quality, it's not the same. Yeah, as you can see it, but the important things it's to get the things working well. I hope it's you can read it. Then we have here, if we look, we had dv over dt, and in the second question we had the expression of dv, that it means this is, we can write it by d of the expression of vr square root of 1 plus p square. This is the expression of here, the expression of v, the velocity, and is as function of vr with phi, and this is d over d phi multiplied by omega. And now if we derive, we have here phi square over d phi, then we get here the expression of E tangential is VR omega phi divided by square root of 1 plus phi square. This is the expression of the tangential acceleration. And now for the determination of the normal expression or the normal acceleration. Here we note it by an. Then we get here an. We have always a equal to an, or I write it as we saw it in the lecture. Then here a tangential t plus an. Then we can write that here a square in magnitude, it's only a t square plus a n square. As I said, the quality with the browser here square. The quality is not good, yeah, but we have to handle with this. As I told you, if I don't find the better way, yeah, to make everything working well, I will shift to zooms, yeah, and we will see. In any case, that it means here in this expression, we have the acceleration. We found it in the second part of the question. We have the expression for the tangential now, and we have to find the expression for the normal component. In this case, we can write that an it's an it's only square root. Sorry, it's not vector. We have an, it's only square root of a square minus at square. Then we have here the expression of an and at. If you remember well, we have a, the total acceleration. It's given by the following expression here. V r omega square root of 4 plus v2. And we have the expression of at, which is given by vr omega phi square root of 1 plus v2, phi square. Then in this case, if we write that we have here vr omega square root here of 4 plus phi square minus phi square divided by 1 plus v square. Then it means here, if we simplify these things, we get the expression of here an equal to VR omega 2 plus v square divided by 1 plus v square square root. This is the expression of an. Then we had now at and an. Then the vector A has the following component VR omega phi divided by square root of 1 plus phi square. And we have the second component in normal direction. It's VR it's VR omega multiplied by 2 plus phi square root of 1 plus phi square. And this is the total expression of A in tangential direction here, and we have this part here, it's in normal direction. Then if we look now how it's come to the expression, that is mean if we draw this, we can say like we have the path that we have here, let's say path like this. That's what we have. We have any point here has one component an, and the acceleration has the normal one in an direction, And we have one component which is tangential to the path, and this is AT. And this is the in the direction of AT. That it means if we look now, what we have this part and this part. Then we get here the expression that the vector is the summation of the two vector an and at that we have here. This is the vector of A. Then it means we have the tangential component in direction of the tangential axis and the normal component in the direction of the normal axis here. And we have the resultant, which is the decomposition of tangential one and the normal one. This is, let's say, for the exercise 1. Now, what I will do the following, yeah, because I see the quality of writing, it's not so good as the previous one, yeah, as this one here. What I will do, it's not a problem of laptop or that, or tablet. The problem is with the software itself, yeah. Now, what I will do, I will use two methods. One, I will get the problem, yeah, using directly the not Microsoft Note. I will shift, yeah, to the browser here, such a way that, yeah, the quality is not good, but yeah, we have to handle this exercise to finish them today. Okay, now I will make here the line and return back to exercise 2. Okay, for the exercise 2, what we have here, we have an industrial robot transport a piece of mass here, M. The robotic arm here can translate and out, that it means can translate in this direction here, yeah, and then return back to this direction of the housing and simultaneously rotate about the main axis here. This axis is rotating. That it means it's translating in this direction or in 2D, yeah, this direction or the perpendicular one, that's making, and itself it's rotating around this axis here. What we have at time t0 that we have the value of the time, it's 0. The arm extended to R0. That it means it's at this position here at time t equal to 0. And the housing spins with angular velocity omega 0. And the mass is pulled inward with relative velocity v0. Now, what we are getting, R0 is 130 centimeter, omega 0 is 1 radial over second, omega dot it's 1/2, 1 radial over uh, second square, which is constant, omega dot. In the radial direction, we have V0, which is 0.1 meter per second, and the relative acceleration is 0.2 meter per second square, which is constant. The question is to determine the absolute acceleration A and the absolute velocity v of the mass m at time t equal to second in polar coordinate system. Okay, and draw all velocity and acceleration components in the diagram. Now, as I said, I will shift to Microsoft Notes on here, and I will use my books, and I hope it will work. If not, I will shift to Mozilla or to the browser to use such to shift to the to solve this exercise. Okay, then we say exercise 2. Then if we look, we said that if you look to later to the slide to compare the formulation, what we had R is defined always R as magnitude multiplied by ER, which is in radial direction, and the velocity V, which is R dot AR plus R V dot AV. That it means now, if we look here, we have two components, which is here, R dot ER plus here, this term here, it's only phi. This is the component of the velocity along circumferential direction. And we have here then as you can see, there is a problem now with this software. I will shift now to the browser. Then we said that here the velocity, the quality of the writing is not good, but we have to handle. V, we can write it by R dot ER plus R V dot EV. And this is will be here. We can write it as the velocity in radial direction, AR, plus here the velocity is circumferential along phi axis. That is means now, if we look to this, that's what we had. You look to the slide, what I make in frame yellow, this is what we use for the expression that here we have VRAR plus VV and we have for the acceleration, this is given by R dot dot minus R V dot square AR plus 2 R dot V dot plus R.
Doctor, we cannot see your screen anymore.
No? Okay, one moment, yeah. Okay, I repeat. We have the velocity here, which is R dot AR plus R V dot EV. This is, you could look to the slide, as I said, the yellow, what I made always in yellow at the end. Yeah, this is the important equation that we need. We don't need the demonstration. This is only to show you how it's this equation, what we use in practice, let's say, to solve the mechanical problem in dynamic. Then we have this expression. This is VR. This is the radial velocity, which is only R dot. And we have VV, which is in circumferential direction, and it's only R V dot. Now, if we come to the acceleration, you look to the equation on the slide, which have R dot dot minus R V dot square, AR plus 2 times R dot V dot, yeah, plus R V dot dot, yeah, in circumferential direction. Now, what we had from the exercise, what it's given that R here given R dot dot, it's constant, and this is, it's only minus a relative, and it's equal to minus 0.2 minus 0.2 meter per second square and we can write that here, if we make now r dot dot constant, that it means if we integrate, this can give now the integration of r dot dot will give r dot, and we integrate minus a relative with respect to time. Then we get here r dot with respect to time. This is equal to minus a relative multiplied by the time t plus constant here plus C1. That's what we had from the given initial condition. Then we have for the initial condition, what we have r dot at time t equal to 0. This is t0. It's equal to minus v0. Then we can get here from this equation that C1 equal to minus V0. That is means we have here now r dot time t is equal to minus r relative time t minus v0. This is the expression for r dot. Now we look to at time t equal to 2 seconds, then we have here r dot r dot at time t equal 2 seconds. Then in this case, we get the value of minus 0 to meter per second multiplied by 2 seconds minus 0.1 meter per second. And in this case, we have this, we get, if we replace, minus 0.5 meter per second. This is for here the velocity in the radial direction. And if we look now to the position, we have R, T, the same principle. We have to integrate this equation here. Then we get this is equal. I tried different thickness of the line that I can get maybe better overview or better writing. Now, if we look to the RT, that it means that R, it's only the integral of R dot dt. It's not better, you know. That it's only the integral of R dot dt. And it means we get here the expression of minus relative multiplied by time square divided by 2 minus V0 multiplied by the time t plus constant C2. What we have R from the exercise, R at time t0 equal to 0. In this case, we have the distance R, it's only equal to R0. This is what is given on the exercise. That it means here we can get C2 equal to R0. Then now, if we replace that, we get here in the expression of R, then R as function of time, it's equal to minus R relative time t square divided by 2 minus V0 multiplied by T plus R0. Then in this case, what we have for 2 seconds, R by the time equal to second. If we are on place, we will get the value of 0.7. That we get here for R at time t equal to 2 seconds, then we get here 0.7 meter. If we are on place, R relative by its value, V0 by its value, and also R0 by its value. Now, if we look to the radial direction, sorry, this is what we got, it's all in radial direction. Now, if we look to the circumferential direction, what we have here phi dot dot, which is equal to omega dot, and it's constant. And in this case, it's given by 1/5 radial square. We use the same principle as for the radial direction. That is means if we want to get phi dot, we have to integrate this expression here. That is means we have to integrate phi dot dot with respect to time. We get the constant of the integration. Then in this case, we have phi dot equal to omega time, which depend on time, and this is equal to omega dot time t at time t multiplied by time t plus c constant of the integration C3. We have the same question that it means phi dot here. It's omega dot, then it means that we get here phi dot, it's only omega. And we integrate this equation here with respect to time, then we get omega dot multiplied by t plus constant of the integration. The constant of the integration is always, we take in consideration the initial condition. What we have as initial condition, we have phi dot at time t 0 equal to 0. In this case, we have the value is given this is equal to omega at time t 0 equal to 0, and this is constant and it's equal to omega 0. Then it means here C3 it's equal to omega 0. Now if we look to here, we have phi dot at time t. This is equal to omega dot time at time t plus omega 0. Then in this case, we get here for time 2 seconds. Then we have phi dot at time t equal to 2 seconds. Then we have here the value we get. If we are on place, we get the value of 4 1 over second. This is for phi dot at time 1 over second. Now, if we look to phi at time phi at time t, the expression of it. Then what we have phi dot here at time t, omega dot t plus omega 0. Then we integrate phi dot, we get phi. Then if we integrate that, we get here phi t at time t equal to omega dot t square divided by 2 plus omega 0 time t plus constant c 4. If we do so, then we have at time t 0 phi at time 0. Then we have here t 0 at time t0 equal to 0. Then we get here equal to 0. Then here we can deduce that C4 equal to 0. Then we get the expression for phi at time t equal to omega dot t square divided by 2. If we integrate the previous equation plus omega 0 time t. This is the expression for the angle phi. Now, if we look to phi at time t equal to 2 seconds, we get, if we are in place in the following expression here, what we get the angle phi h5 radial. Then we get here, if we substitute all these things, phi dot r, yeah, r dot, and so on, then we are in place here on the following expression here, we get the velocity v and the acceleration a at time t equal to 2 seconds. That is means we have here now v at time t equal 2 seconds. This is will be equal to, I will write without unit, then it's minus 0.5 multiplied by ER plus 0.7 multiplied by 4, and here FE, then we get here minus 0.5. ER plus 2.8 E phi. This is expression for the velocity. And if we get now for the acceleration, we have A at time t equals 2 seconds, and we get here minus 0.2
Doctor, I have a
minus,
question.
yeah,
So when you
yes,
solve these questions, so we have to
yeah.
show you all the steps from where we get the equation, or we can write the last equation only and plug in the numbers?
When you solve these equations, no, you have not to, it's only to show the step, because it's now I'm doing it this for you, yeah?
Yeah, so on the
You
exam,
understand?
we could,
In the exam, for example, if it's asked to give V at time t equal 2 seconds, what we have to look, it's only this equation at the end, okay?
okay.
And which equation you used for this.
Okay, so we don't have to write how we get this equation.
No, how we get, I told you already. Because this, you see here, yeah? This equation here, yeah? This is, you have to remember. Because
Okay,
on
yes,
the
thank you.
slide, on the slides are given in yellow color.
Okay, thank you so much. Okay.
Yeah.
Yeah, thank you.
You don't need to make a demonstration of how we got them and so on. What I need is, because when you go to the industry, they don't need to show how to go to these equations and so on. You say the velocity for such kind of the problem, it's given by the following case. For example, if you choose to get polar coordinate system, or if you use Cartesian coordinate system, there is another description of this velocity and acceleration. That is means this, there is memory books, let's say, where you have all equations, yeah? Like in mathematics, you don't need to demonstrate, you know only how to do this, yeah? Which equation I need and how to apply them. This is the aim. Yeah, got it?
Yeah, thank you so much.
You're welcome. Now, as I said, that here, if we go to A is given by this equation here. Yeah, here. And you have only to replace each value, r dot dot, yeah, r phi dot, r dot phi dot phi dot dot, yeah. You replace each value at time t equal to second. And if you replace, you will get minus here 0.7 multiplied by 16. And this is, it's in ER direction plus 2 times minus 0.5 multiplied by 4 plus 0.7 multiplied by 1.5. And this here in circumferential direction. That it means if we replace everything here, we get A at time t equal 2 seconds. We get minus 11.4 meter per second square AR plus 2.95 meter per second square before. And this is the vector acceleration. And here, as we said, the acceleration has also the tangential, the radial one, and the circumferential one. I want only to tell you that it's here by such problem. It's not easy to handle them in Cartesian coordinate system. Okay. For this, we make distinction between radial, let's say, polar coordinate system when we have circumferential motion and also radial motion. Then it's more easy to do this. We have the equations are already given, but if you handle in Cartesian coordinate system, that it means if you use the Cartesian system, you have to project each component of the acceleration, the tangential one, yeah, circumferential one, you have to project it along the axis X and Y. And this is more complicated, yeah, to describe such motion, yeah. If you are scaring about the examination or that, I will facilitate the case that you tell use such coordinate system, the appropriate one, yeah, that to solve problem, let's say, yeah, in time. Now, if I have to sketch this component, if I show you that now here we have the point, yeah, of the mass m rotating with omega, and in this case that we have our arm, we have our mass here, m. Now what we have all components now. If I draw this, I will use different color. That's what we have here. We have R phi dot. We have two R dot phi dot, and we have R phi I close it once moment. And here R phi dot dot. This is the description where, as you see that here, if I look now to the equation, this all things are in EFOW direction. That is means now if we look to EFOW direction, we have this component that is means EFOW direction for the velocity v, we have r phi dot. This is circumferential one. And for the acceleration, we have the two terms here, 2r dot phi dot plus r phi dot dot. This is in circumferential direction. Now, if we look to the radial one, then it means that we have here this is r dot. We have also in the same direction r dot dot. and we have R v dot square.
Doctor, we can't
And
see
this is
your screen.
no. Okay, one moment. Okay, I repeat that we have here R phi dot. This is the opposite one, and as the opposite direction of E phi. We have 2 times R dot phi dot, and we have here R phi dot dot. This is R only the component in the circumferential direction of what? Of the velocity here, R phi dot, and the 2 components here of the acceleration in circumferential direction, where we have 2 times R dot phi dot plus R phi dot dot. The same principle for radial direction. We have R dot, we have R dot dot, and we have here R phi dot square. This is all 3 components here for the velocity here and for the acceleration here are given in E R direction. Okay, this is what we have now. This is the description to see the direction of each part. Here you see its opposite direction, 2 times R dot phi dot, yeah, which is negative. That it means here we have 2 times R dot phi dot. It's opposite, yeah, to the E phi direction. Okay, this is for the second exercise. Only I want to tell you that this, what I am writing here, yeah, the note, I will put it on Moodle, and before to put it on Moodle, I will work on it. That it means that I will use directly the Microsoft, not the software itself, without these things from browser or my notes. I will make it properly, yeah, and I will put it on Moodle. Be only patient that maybe I will not do it today, yeah, only if I can find time. Maximally, you will get it tomorrow evening. Okay, that it will be more clear. You have the description of these things on, I will put the video on YouTube. And for the details of the solution, to repeat it at home, okay, you will get the notes here, the details of the solution properly, okay, then you will get it either directly by the note or you will get it by as PDF file. Okay, now coming to the third exercise. And now if we come to the third exercise, what we see nearly the same problem as the second one. The difference here, we have three-dimensional problem. And we see how to make the things when we have, let's say, the Cartesian system X, Y, Z, and following now, if we use the radial cylindrical coordinate system with the angle xi, yeah, it's only matter of notation. We can replace it by phi, okay? And what we have here, we have the mass m, okay, along a helix such that the temporal change of the angle c remain constant. That it means we assume that xi is constant. The time of the helix, the size of the helix is h here, this distance here, and at time t0, the mass is located at r here, at this position here, r, and y and z are equal to 0. That is, means we start from this position here, at this point here, where we have in z and y 0, in x and y, sorry, in z and y is 0, 0, and x, it's only the radius of this circle here. Okay, now it's asked for in Cartesian coordinate system, the position vector r as function of xi and r as function of time t. The velocity v, t, and its magnitude v, the acceleration vector a as function of t and its magnitude a, and determine the unit vectors of the accompanying three axes. That is, means it's z, a y, and a x. And to define the component of the acceleration in tangential direction as well as in the normal direction. Now, coming to the solution, I try to make it clear with this problem of writing. Now, we have for exercise 3, it seems it's become more awful. Now what you hear, it's given x vector at time t 0, it's equal to this is time t0, it's in x direction, it's r radius, 0 and 0 in y and z direction. Now what we have, xi dot, this is constant. And xi dot, as I said also in the previous example, it's only phi dot. Yeah, it's matter of notation. Then in this case, it's only the angular velocity omega. And if we make the integration, then we get xi equal to omega time t plus c1. Now what we had from the initial conditions, C1 is equal to 0 because we have the fact that C at time t0 is equal to 0. Then we get here C1 is 0. Then we have Xi, it's equal to omega time t. This is the expression of Xi, the angle. Now in Cartesian coordinate system, we have the position vector r. We can describe it by here r is function here of Xi. We have the three components along x, y, and z. Then we have r, the radius, cosinus Xi. We have r sine Xi, and we have z along Xi. Set Xi here as function of Xi. We can describe it using the fact at 2 pi we have the high h. That it means we can get h divided by 2 pi multiplied by Xi. Now we can get here the vector r. It's only to replace here as Xi, it's omega t. Then we get here r vector, the position, r cosine omega t. We have r sine omega t, and we have h divided by 2 p omega t. This is the expression of r here as function of time t, and here r as function of the angle c. Now, if we look to the velocity, velocity is the same principle that here velocity we have v by definition as function of time. We have r dot. It's time derivation of the vector position. And if we make now here each component here, we have to derive with respect the time. Now, if we get this, we get here minus r omega multiplied by sine omega t. The second component along y direction, we have r omega cosine omega t. And we have h over 2 pi omega. This is the velocity. And now, if we look to the magnitude of this velocity, we have only to take these three components. That is, means we have v, which is the magnitude of the vector v, as function of time. That is, means we have here, by definition, v, I write in, to make it more clear, vx square plus vy square plus vz square. This is the magnitude of the velocity, that it means we have to take this component along x direction, then bx squared is minus r omega sinus omega t square plus this part square plus this z component square. Then we will get here omega r square root of 1 plus h 2 pi multiplied by r. Square. This is here. This is the magnitude here, v, and the acceleration vector is the same principle here, a. I write acceleration then we have here a as function of time t. It's only the time derivative of the velocity vector and this velocity is only r dot, that is means it's r second time derivative of the position vector. Now if we look to velocity, we have to make the derivation of each component with respect to time. Then we get here a minus r omega square cosine of omega t. The same here, minus r for the second component, omega square sine and here omega t. And for the z in z direction, As you can see here, the component, this is constant. In this case, it's time independent. Then in this case, we have here 0. That A, if we take the same principle, A magnitude, it's only absolute value of A as time t, and here the same principle. We have A along x direction square plus A y direction square plus A z square. And this is square root. Then in this case, we get r from plus each value that we got r omega square. Then if we search now for second question, the unit vector of the accompanying three axes, what we get from the first part of the description of the velocity, we know that the velocity v, it's always given in tangential direction. That is means we have v in tangential direction. That is means we get here the components of the unit vector A t, and this is, it's only the vector v divided by v. And here v, it's only the magnitude of the velocity. Here what we got here. Okay. Now if we're on place, we get here A in tangential direction equal to 1 divided by the square root of 1 plus h divided by 2 pi r, and this square, this is square root. And here we have the component minus sine. omega t, we have cosine omega t, and we have h divided by 2 pi r. This is the expression of the tangential unit vector or the basis vector. Now, if we look to the normal vector, what we have, we know that En it's always perpendicular to ET. That it means now what we have, we start from the acceleration, and what we get here, if we have A, we know for the velocity, there is only one component, which is the tangential one, because the velocity always follow the direction, it's always tangent to the path. But the acceleration, we saw it in the lecture, that has always two components, the tangential one and the normal. Then we use this principle that to get here, we have A T, which is the tangential one, plus A N. And this is the normal one. That it means if we decompose it, we have A tangential along tangential axis plus A magnitude and along N direction. Now the question, we have ET, we can get it, yeah. We had it by definition. It's easy. Why? Because it's only V, yeah, dot, the magnitude V dot. But the second one that we have here, this is the problem is to get the normal one that we have here. It's equal to V dot A T along tangential direction plus V, let's say phi, or we call it alpha for the moment to make distinction with xi, that we have phi dot alpha dot A N. Then we looked at here A N, it's only V alpha dot, yeah. Alpha dot we haven't, but AT, it's only V dot. Then it means if we look now, it's only this component here, the magnitude, then we can get the acceleration in tangential direction. Then it means here now we can write that En is only V alpha. Yeah. Then we can get here V. This is the component En. Now we can write here that En is only here equal to V E dot T. And with here E dot T, it's only here we can write it by alpha dot En. If you remember, we said that in polar coordinates we have AR vector, unit vector, it's only phi dot phi. The same phi, it's only minus phi dot er. It's the same principle that we are using here. And we can say that here En as vector it's equal to the vector acceleration in normal direction divided by the magnitude of this vector. Why? We have here, this is En V alpha dot, and V alpha dot here, this component here, it's only En. Then it means always the unit vector can be described by by the vector divided by the magnitude. This is it's known in vectorial vector calculations. Now, if we do so, then we can get here by definition. Now, it's only here En. En, it's only V E dot T. That it means we get here V E dot okay. The things it's not reacting. Now, we have E dot T divided by V E T vector dot, but its magnitude. Then it's come to here as v. Here the velocity is scalar, yeah. Then it come out of the magnitude. Then we can simplify it. Then we get directly E dot t divided by its magnitude. E dot t. Okay, we have only that the expression E dot t. We have et here. We have to make the time derivative of it. Then we get here the expression for E dot t, and we make also the magnitude. We take the same equation. We take the first component in x direction, y direction, z direction, square root, and we